So for number 15, it's asking how many arrangements are possible for the letters in the word omega. And so this is just like a problem where, let's say you have 5 students and they need to be arranged in a line. How many different ways can they be arranged? So we have student 1, student 2, student 3, student 4, student 5. You can think of it that way. All right, so this would just be 5 factorial because any of the 5 students could occupy the first position. Once one of those individuals is placed, any of the remaining 4 could occupy the second position, any of the remaining 3, any of the remaining 2, and the last person in that particular order. So that would give us 5 factorial, which is 120. Now for alpha, you see that we have a repeated A. Right? So just a quick example, let's say I wanted to rearrange the letters in the word alpha. One way that I could do that would be to switch this A with this A. If I do that, I wouldn't get a unique word. It would be the same word. Right? So switching the order between those 2 A's would not impact anything. Right? So that would be an extraneous arrangement. Right? So let's say I had LPHAA. Another arrangement would be swapping these 2 A's, LPHAA, same quote-unquote word, but it's based off of a swapping of 2 letters. Right? So we have a rearrangement, but it didn't lead us to a unique word. So we're always going to end up with twice as many outcomes as we should have. So the way to handle that would be to count up the letters in the word alpha. There's 5 letters, so 5 factorial. Without restriction, that would give us 120 arrangements. But we divide it by, well, in this case 2, but we're dividing it by 2 factorial because the 2 factorial gives us the number of ways to rearrange the letters A and A. All right? Number of arrangements of A and A. All right? So if the A occurred 3 times in the word, then we would divide by 3 factorial. If it occurred 10 times in a word, then divide by 10 factorial. All right? So in this case, we're getting 120 divided by 2, which is 60. All right. Number 16, 8 boys in a class on our first day of school. So this is basically how I started the previous problem. How many ways can we rearrange these individuals? That would be 8 factorial. All right, so 8 factorial. I'll just do it on Desmos here. Math probability option 4, I believe, if you're using a TI. Most people would be. 40,320. All right, so 2 of the boys are twins that must be kept together. All right, so it's kind of like a repeated letter in a word. All right, so if we have, in fact, you could even write a word, with repeated values. So like an 8-letter word, for example, where 1 letter is repeated. All right, but we can even say, all right, we have the twin, the other twin. I don't know how to describe that, but the 2 twins, all right, and then somebody else. All right, so student 1, 2, 3, 4, 5, and 6. All right, so that's a total of 8 people. Another arrangement would be swapping the 2 twins. And the previous problem is we would get a unique arrangement if we swap the 2 twins. Right? They're not interchangeable in the sense that the letters A are, and you would still get the same word alpha. All right. If we change the position of the 2 twins, yeah, they may look alike, but they're not the same people. All right. So we can kind of treat it like that word question from number 15, but only to a certain extent. Here, I'd have to look at this as, we got Tommy and Timmy, whatever you want to think of. Right? But if their position changes, maybe Tommy's in the first position and Timmy's in the second position initially, but swapping the order would give us a unique arrangement, all right? So we would look at this as saying, all right, well, we have two individuals that kind of follow their own rules, Tommy and Timmy. So that's 2 factorial because we have arrangements accounting for just those individuals. And then we have the other 6 individuals that follow their own rules, all right? So that's 6 factorial to determine how many ways those individuals could be arranged. But nobody ever said that Tommy and Timmy needed to lead off the line. Right? They could be at any position within the line as long as they're grouped together. So if we have 8 positions, 2, 3, 4, 5, 6, 7, I'll throw the 8th one here. We could have Tommy and Timmy occupying the first 2 positions, the second 2 positions, the third 2 positions, 4th, 5th, 6th, or 7th. All right, any of these positions, any of these rings that I just drew would be a location in which the 2 individuals can be grouped together. All right, there's 7 ways that that can happen. So I would take this result and multiply it by 7. All right, so 7 times 2 times, I believe 720 is what 6 factorial is, so 10,080. All right, now if the twins always fight, all right, how many ways can they be arranged so that they're always kept separate? Well, these are the ways in which they would always be kept together. These are the ways people could be arranged without restriction, so just subtract the 2. So that would be minus the 10,080. So we're looking at, so 40,320 minus 10,080. So 30,240. All right, and so then number 20, what's the probability a Major League Baseball player with a career hitting success rate of .3 would get his first hit of the season on his 30th attempt at bat? Well, assuming, well, you have to make an assumption of independence here. Otherwise, there would really be no other way to do this. If his first hit is going to happen on his 30th attempt at bat, that would mean that he would have to fail the first 29 times. All right, so fail 29 times, then succeed. All right, so the probability of failing 29 times would be 0.7 raised to the 29th power. And then the probability of succeeding would be 0.3. So 0.7 raised to the 29th times 0.3. We get this disgusting decimal. Approximately 966. So 5 zeros followed by 966.